We're on page 305. We're finding indefinite integrals. We're going to use the substitution method or the change of variables method, whichever you want to call it. It's called both. And this time on 48, they give us a trig function. And that's a game changer sometimes, and it is in this case. Because what we've been doing so far to choose u is we've been finding a quantity with an exponent on it. You know, that's straight out of the guidelines. That's, number one there. That's not going to work here. All right? But what we want to do instead then, so the next thing down the list of what am I looking for first when I'm trying to figure out what u equals? Quantity with an exponent. All right, that's always going to be the first thing we look for. And then next, if you have trig functions, then let's look for the theta part of the trig function, the angle part. So x squared in this case. Okay? So let's try letting u equal x squared. And then if you remember, what we do next is we have to figure out what du equals. So we always compute du. It's not an automatic thing. Every du is different, isn't it? Every time u is different, du is different because we compute it. It's the derivative of u with a dx at the end is what it amounts to. Okay? So you take the derivative of both sides, so you'd get du dx, and then you get 2x for the derivative of x squared, and then we do the little algebra trick, and we multiply both sides by dx. So I expect you to be able to go straight down your paper just like what I've got showing on the screen. Okay? So du equals 2x dx. Well, look, that's good, because if I'm making the substitution, and I'll do it for real here in a minute, but mentally you need to be thinking what I'm getting ready to show you here. Think, okay, that's the sine of not x squared, but u, so that takes care of that part, but I still got to replace x dx. Now, it would have been really sweet if du had equaled x dx, but any multiple of x dx is good enough, isn't it? Okay? So it's a multiple of x dx. It's 2x dx, but I want x dx, so how do I turn 2x dx into x dx? Multiply both sides by 1/2. Divide by 2, but multiply both sides by 1/2. So 1/2 du equals x dx. So that means x dx that I still needed to replace is going to be replaced by, and look, I know I'm going to factor a constant out and put it in front, right? So let's save ourselves a step and put the constant in front, 1/2 du. Have we done it? Yeah. So therefore, our integral is now 1/2 times the integral of the sine of u du. Now, this only works if we know what the antiderivative of the sine of u equals. I do. Do you? What's the antiderivative of the sine of u? Negative cosine u. So, it's been a while. Let's rememorize those antiderivatives. Rememorize them. Plus c. So I've got a couple things I want to do next, right? I want to multiply the 1/2 times the negative. It's a negative 1, really. Get a negative 1/2 cosine of, and then I also want to replace u and put my answer back in terms of x. So replace u with x squared, because that's what it equals. So negative 1/2 cosine x squared plus c. All right, so we let u equal a quantity that has an exponent on it. We let u equal the theta part of a sine function, or of a trig function. Because we don't have any idea what the antiderivative of sine of x times the sine of x squared is. It's a product. It's got an x squared instead of an x. It's just a big fat mess. Okay? All right, so that's probably the only two things that will ever happen, right? U will be a quantity with an exponent on it, or U will be the theta part of a trig function. Boy, I wish that was true. Number 49. Now, let me do this one wrong first. Maybe you want to write down the wrong way just so you can put a big X across it in a minute for your notes, or maybe you don't. That's up to you. But following what we just got through doing, I'd say, okay, I don't see a quantity with an exponent on it, but I do see a theta part of a trig function. In fact, I see that twice. So I'm thinking, all right, let's let u equal 2x. So that means I could write that as the sine of u times the cosine of u. All I need to do now is hopefully du will equal dx. And so I'll say, okay, then du would equal, what's the derivative of 2x dx? 2 dx. Like, oh, okay, awesome. If du doesn't equal dx, but it's a constant, it's a multiple of dx. So I do 1/2 du equals dx, which means, so I've already replaced that with sine u, cosine u, replace dx with 1/2 du, and I'm in business. What's the antiderivative of cosine of u, or of sine u times cosine of u? We don't know. We don't know. Sure looked like it was going to work, didn't it? But it didn't. Why? Because the new integrand we came up with, we don't know how to find its antiderivative. Everything worked out great. The du part worked out and all. The trouble is the new integrand is one we don't know how to find the antiderivative of. So we try something else. Now, sine and cosine, with the exception of a negative sign, aren't they derivatives of each other? Okay? So really? Well, so here's what I'm going to do then. I'm going to let u equal the whole thing of that trig function, sine of 2x. Leaving off the cosine of 2x for a minute. So let u equal the sine of 2x. Now, if I'm doing a dry run on a substitution over here, instead of the sine of 2x, I can put u. That means I've got to replace still the cosine of 2x. Now, it's no fair doing another u, right? I've got to compute du and then somehow algebraically make it all work out, or I got to try something else. So, what is du? What's the derivative of the sine of 2x? What's the derivative of cosine of x? Or of sine of x? Cosine of x. So what's the derivative of the sine of 2x? Cosine of 2x, chain rule it, times the derivative of 2x, times 2. So it's the cosine of 2x times 2, or 2 times the cosine of 2x, dx. Now, that's the kind of thing, this is kind of weird, because months ago, if I'd asked you what's the derivative of the sine of 2x, that would have been an easy problem. But we've done so much since then that it's like, okay, derivative or antiderivative? Chain rule. What's the chain rule? Right? I mean, so something that, and math doesn't usually work that way, does it? Usually it's something that used to be hard to get simple. Something that used to be simple now seems hard just because it's been a while since we've done it. But the derivative of the sine of 2x, you got to use the chain rule on it. So it's the cosine of 2x times the derivative of 2x. Okay? dx. All right. Well, that's really close to what we need it to be, isn't it? We need to replace the cosine of 2x dx. So multiply both sides by 1/2. And now we can replace the cosine of 2x dx. What are we going to replace the cosine of 2x dx with? 1/2 du. We're going to replace that I just circled in green with 1/2 du. And when we do, we get a very simple integral problem. So we leave the 1/2 out in front. We take the antiderivative of u, so we use the power rule for antiderivatives. So that'll be 1/2 u squared. Don't forget the plus c. And now we've got to do two things. We need to multiply our constants together, and we need to replace u with what it equals. So we multiply 1/2 times 1/2 and get 1/4. Replace u with what it equals, the sine of 2x. Still plus c. And I guess I'll take that as your answer, but it's not really the proper notation for that, is it? If you have the sine of 2x, all that squared, that's the notation that's sine squared 2x. Yes. From here to here. All right, so copy down the 1/2, and then the antiderivative of u. I added 1 to the exponent, and then I divided the coefficient by the new exponent. Okay? All right. So, try to let u equal a quantity with an exponent on it. With trig functions, first, try to let u equal the theta part. But trig functions do this sometimes. Sine and cosine do, anyway, where they're the derivatives of each other. So let one of them be u, and then the other one's going to come out with the du. Technically, I could have let u equal the cosine of 2x and worked this problem out. I would have gotten a different answer. It would be an equivalent answer, okay? But it would have looked different. So, and so which do you choose then, sine or cosine? I always choose sine. Yeah, always. That's a strong word, isn't it? I did this time. Okay. So, quantity with an exponent, theta part, an entire trig function. Notice I didn't say the entire integrand, but an entire trig function, the sine of 2x. Okay? All right, getting a little more complicated than you wanted it to, isn't it? Number 64. Find the indefinite integral by the method shown in example 5. Now, very few students are going to now look back at example 5. You are now, because I just pointed out that human nature says, I don't need no stinking example 5. I can figure this out. All right, example 5 gives us, just let me work this one. Once I've worked this one, then maybe you can make example 5 make sense to you, okay? So, you're getting a big flashing red light warning, uh-oh, aren't you? When they tell you to, they don't even tell you a method with a name on it. It's just the method shown in example 5. You need to be thinking, oh, okay? So, we start off really simple with an integral sign of x times the square root of 2x plus 1 dx. All right, let's do what we've been doing. Quantity with an exponent on it. Let's try that. Just so you know to go ahead and write it down. It's going to work. It's not going to look like it's going to work, but it's going to work. Let's let u equal the quantity that has the exponent on it. So let u equal the quantity, 2x plus 1. Which means, if you're keeping score at home, so far my substitution would look like this. That would be written as the square root of u, wouldn't it? So all I have left to replace is x dx. Well, the dx kind of automatically gets replaced, doesn't it? But I got to worry about turning this thing into x dx. All right. If u equals 2x plus 1, what's du equal? 2 dx. Okay. Not really what I wanted. I wanted an x dx. And I didn't want a 2. So we're used to doing this next thing. Multiply both sides by 1/2. So I get 1/2 du equals dx. So that means I can now replace the dx with 1/2 du. And you might be thinking, well, okay, I'll just leave that x. I don't know what to do with that. I'll just leave it. I'll just sneak it in there. He'll never see it. It'll all be okay. So you know that's not true, right? we got to get rid of the x. We can't work an integrand. We can't work an integral where the integrand has 2 different variables in it. We can't do it. Do what? All right, here's what we got to do. I got to replace that with something that has u's in it instead of x's. Look right here. Solve it for x. And you will come up with something with u's in it. So u equals 2x plus 1. So that's what you couldn't tell it as I was uncovering this, but that's an arrow pointing me down to here. So subtract 1 from both sides, and you get u minus 1 equals 2x. Multiply both sides by 1/2, and you get 1/2 quantity u minus 1 equals x. So, as ugly as it is, guess what we replace x with? We replace it with 1/2. So that's another 1/2 times the quantity u minus 1. Now, all of this has been a big fat waste of time if we can't find the antiderivative of what we now have. And we can't yet. But that square root of u is really u to the 1/2, correct? If I distribute u to the 1/2 times u and u to the 1/2 times -1, this is actually a polynomial is not right because it's got an exponent of 1/2. But it's a function we can actually take the integral of one term at a time. So we've got this. Let's multiply the 1/2s together and get 1/4. Might be easier actually just follow me from up there. And then distribute that square root of u. Distribute that u to the 1/2. U to the 1/2 times u. Add the exponents. Get u to the 3/2. U to the 1/2 times -1. Negative u to the 1/2. And now we've got something we can find the antiderivative for. So you with me? All right, so hopefully, well, I'll say that in a minute. All right, so here we go. Keep the 1/4 out in front. The antiderivative of u to the 3/2. Power rule it. Add 1 to the exponent. 3/2 plus 1 is 3/2 plus 2/2 is 5/2. Then you got to divide by that new exponent. Dividing by 5/2 means multiplying by 2/5. All right, then we move to the negative u to the 1/2. Add 1 to its exponent, 3/2. Divide by the new exponent. Well, dividing by 3/2 is the same thing as multiplying by 2/3. So the negative coefficient times 2/3, -2/3, plus c. Okay? All right, so we've still got quite a bit of of work to do because we need to change the u back to 2x plus 1, and then we need to decide, because usually when we start in radical notation, we prefer to end in radical notation. So we got to decide, do I want to make that 2/5 2x plus 1 to the 5/2, or 2/5 times the square root of 2x plus 1? Then I got to decide, do I put the 5 there or do I put it there? So on problems like this, we're all going to come up with something a little bit different, or there's going to be a few different answers. If it's on a AP test, or if I give you a multiple choice test, then you got to figure out which one is the correct answer. They're not going to give it to you both ways, right? But for now, I'm really okay with you leaving that one in exponential form. And I'm also okay with you not distributing that 1/4 through there. So I didn't really simplify this one, did I? I just replaced u with what it equals, 2x plus 1. And even if you do distribute the 1/4 through there, remember, you don't have to multiply it times the c and call that 1/4 c, because we don't know what c is anyway. Technically speaking, if I did, it would change from like a c to a c1, something like that. But nobody, it doesn't matter. That doesn't hurt anything. Any questions on 64? And I do think you probably needed to see an example of that. I don't think you'd have figured that out on your own. Yeah. Yeah, just a minute I will. All right. Hopefully what you've figured out from these examples I've done today is you kind of don't really know if what you're trying is going to work out. Because, which one was it? This one, letting u equal 2x sure looked like it's going to work out. And it didn't. This one, I mean, you had to be thinking at some point in here, this isn't going to work. I did when I worked it out. I thought, crud. I don't know if I'm wasting my time or not. Turns out I can make it work. Okay? So you got to be patient and you got to be persistent to get these done. And look, you got to be willing to miss a few. Don't just stop saying, well, I don't know what to do. You got to be willing to try it and get it wrong, because you're going to get some wrong. Just like I got them wrong when I was learning it. Just like I get them wrong now. And by wrong, I mean the first thing I tried didn't work. Okay? That still happens to me. I've been doing this for a million years. And I'm still not always able to tell exactly what u is supposed to equal to make it work. Okay? That's just the way it is. Okay? So stick with it. Now, you're ready to do 2 different assignments. All right, so you know the assignment now. Let's take a look at number 19. Let's do this too. Oh, what did I do? All right, I don't want you to get distracted with these other things. Let's just look at 19 here. All right, because it does look a little different when it's got a denominator. So we still want to let u equal a quantity with an exponent on it. And in fact, usually, if you have whether it's actually truly a rational function like this one or just one with a numerator and denominator, if you have two different quantities, if you have a quantity in the top and one in the bottom, usually it's the one in the bottom that works. Usually. Okay? Now everything, if I ever say always while we're talking integrals, say, Mr. Jackson, you said always. And I'll say, oh, I didn't mean always. Usually. Okay? It's the quantity in the bottom, which works nicely here. So we let u equal 1 minus x squared. And if u equals 1 minus x squared, take the derivative to get du. So the derivative of 1 is 0. The derivative of negative x squared is negative 2x. Don't forget your dx. Well, now look, if we're writing this out as we go, that means I have a u cubed in my denominator, doesn't it? And I need to get x dx, because that x is in the top. That's just a regular x, right? A number in the numerator is just a regular old number, so I need to replace x dx. I've almost got that. All I got to do is multiply both sides by negative 1/2. So I'll multiply both sides by negative 1/2. So that means the x dx gets replaced with negative 1/2 du. Now, look what I've got written there in red. That's just silly, right? There's no numerator. What's the numerator? 1, right? 1, because times 1, 1. Multiplying by 1 doesn't change the value of anything, does it? So you'll never have a blank numerator. It's 1. Just like if I write the number 5 and I say, what's the denominator? You don't say blank. You say, oh, the denominator's 1. Okay, so same thing. You never have a blank numerator. It's a 1. So that means I've got the integral, or I've got negative 1/2 times the integral of 1 over u cubed du. And at first you think, well, that's no good. I don't know what to do with that. And then you remember there's such a thing as negative exponents. 1 over u cubed is the same thing as u to the negative 3. And now we're in business, aren't we? So you got the negative 1/2 in front. Then you use the power rule for antiderivatives. Be careful here. When you add 1 to negative 3, you don't get negative 4. You get negative 2. Then when you divide by negative 2, that's the same thing as multiplying by negative 1/2 plus c. Now, negative 1/2 times negative 1/2 is positive 1/4 times, and then u to the negative 2, that's too easy to simplify. Make that 1 over u squared plus c. So then our final answer, we have a numerator of 1 because 1 times 1 is 1. We have a denominator of 4u squared, but u is 1 minus x squared, so 4 times 1 minus x squared squared plus c. Yeah. On 64, when we did that, when we did our du, it didn't have an x in it, so we had to go back and get it ourselves. On this one, we've got an x in the du, so it takes care of it. You can see the difference? All right, there is something else I'd like to show you too. Look here at number 27, or 26 and 27. Look what I've written out there. No u. I just want to save you a little trouble. You can work those without a u. You've got to do some algebra manipulation first. On 26, that 1 over 3x, quantity squared, make that 1 over 9x squared. Make the 1 over 9x squared 1/9 x to the negative 2. And you can take the antiderivative of each of those terms as it's written. On 27, and I don't even know what I would let u equal to make number 26 work. On 27, I worked it without a u, and then I figured out I could also work it with a u. That doesn't happen all that often, where either you can use substitution or not. So they give you just enough of these that don't require a u to keep you on your toes. I hope that's all it does, is keep you on your toes and not frustrate you to death as you're working 26 through 32. As you're working 26 through 32. I hope the fact that those don't need a u doesn't make you too frustrated. 26 through 32. Oh, 34. 26 through 34. Sorry. Yeah. The only one I found of those that I used, maybe I quit trying to find a U after 27, but 27 is the only one I worked two different ways, with a U and without one. The others, no U. And I really did want to warn you about that, because that will mess with you. Once you finally think you're getting the U thing down, and then you run into a bunch of problems where they don't use one. Now, after we've done this for a couple of days, I expect you'll be able to deal with finding a U, not finding a U, doing whatever you got to do, but that's going to get you. So you can see what I did here. I didn't use a U on those. All right? Yeah, Preston? Okay, pick one. I lost you. Yeah, it still comes out as a 1, because we'll let U equal 1 plus x to the 4th. So that give us that, right? And then we've still got to replace the x cubed dx. Well, it turns out x cubed dx can be replaced with 1/4 du. You can't leave it blank. It's got to be times 1. All righty? Yeah, we definitely will. All right, I think you got enough to keep you occupied for a while.